walk back since I brought a jacket. That way, life will prove I was foolish for bringing jackets. Okay. Last time we were talking over Lagrangian Mechanics. If you remember, the basic idea of Lagrangian Mechanics is we wanted to look at energy. Really kind of what we're doing, instead of the classic Newtonian stuff, where you kind of take a look at, you know, where are all the forces, and then you have to take a look at what the forces end up doing. So you need to worry about the coordinate system for the forces and for the resulting motion. Then you have initial conditions, all these boundary conditions that go on. What we really do with this one is we're taking a look at kind of two instants in time. We're saying, okay, those are 2 points it goes through. Then we want to take a look at the integral of that, the energy across that, the Lagrangian, you know, to count between them, and we say that's a minimum. In order for that to work, that requires, for that to be a minimum, let's take a derivative. That's why we have these derivative equations. Now the neat result of doing this is, we only really have to consider the generalized coordinate system that the motion lies in. Right? So that was kind of the advantage we went up. We didn't have to worry about the coordinate system of the forces and all kinds of other stuff. We just had to worry about the motion itself. What was the energy? Okay? And we said, you know, this is kind of a more generalized way of looking at it, gave us a nice way to get differential equations of what the motion is. This is our end goal. Our end goal is to have a nice, easy way to get differential equations for the motion of a system. The reason why is, second half of the course, we're doing control systems. We're trying to figure out how to make some system we're doing that's described by a set of differential equations behave in a particular way. To make an arm move at a particular rate or whatever it is, in order to know how to make it move at that rate, we got to know not just where to move it to, we have to know the time instances to move it at. We have to know how much force or torque, depending on, you know, whether you're doing prismatic or whether you're doing a revolute joint or whatever. We have to know what to apply to it. Right, so that's what the idea of the control problem is. So our whole goal here is to get a differential equation that accurately describes the motion of our system. Once I have that, it becomes the second half of the course's job to figure out what to do with it. Our job right now is to figure out what is it accurately so we can act on it. Okay, so does the basic goal make sense? Let's start off with a really simple, because we didn't do any examples if I remember correct. So let's start off with a really simple example. You can't get too much nicer than this. Physics always starts with it. I have a mass in a gravitational field, and I drop it. Okay? Now normally we'd write all kinds of forces and all kinds of other ugly stuff, right? Sure. However, we're going to do this really easy. Right? We're just going to say, this is where my coordinate system is. This is y pointing up. Right? Our motion is going to be purely in the vertical, so I'm only going to worry about the vertical. So I can ask you the question, what is the kinetic energy of that ball at any particular time?
1/2 mv squared.
Right? It's 1/2 m, but the velocity in particular is y dot squared, right? There's nothing in the x.
Right.
So it's only the y direction. So that's my kinetic energy. What's the potential energy? Assume that this is my 0 point right here.
mg1.
It's mgy. Okay? So that's my potential energy, right? So I've got my kinetic and my potential energy as, you know, this is getting smaller, going down, right? So away we go. We've got our Lagrangian. Let's take the derivative of it. All right, now remember, what we're doing is we take the derivative with respect to time of the partial with respect to, in this case, it's our y dot, right, minus the partial with respect to y in this case. It's our generalized coordinate system. In this case, I only have y and y dot, so I'm just ignoring the x dot, the rest of it. Right, if I had some theta, I'd have it with respect to theta and theta dot. Right? So whatever my variables are, I take the respective derivatives. Good? Mm-hmm. Okay, so let's go through and take a look at it. All right? And we say that when we apply this to whatever our Lagrangian is, That must be 0 for a system that's in equilibrium. And this is what we're trying to get down to, right? Nice system as it goes. Now, what happens here? Well, let's take a look first off at the partial with respect to y. What do I get with the partial with respect to y of this?
Minus mg.
Right? So the partial with respect to y, this does not involve y. Remember, it's a partial. Right? So the partial with respect to y only happens here. Right? So I've got a minus mg, and I want the minus of that, so I get mg. So that's minus the partial with respect to y. We agree? Mm-hmm. So I took the partial with respect to y, that's minus. Right? This is y dot, so that term's a constant, it goes to 0. Right? I get minus mg from this one, negated, I get mg. Good? Okay. How about the partial with respect to y dot?
And y dot.
Right? So I get 2 times the half, just goes away. So I get m y dot. We agree with that? Mm-hmm. Then I have to take the derivative of that expression, m y dot. I have to take the time derivative of that. So what do I get? Time derivative of that. Mass is not changing. We're assuming we're not relativistic. I realize your mass can change in relativity. But in our case, we're not. So I get my double dot. We agree? Mm-hmm. After I've taken this one. That has to be 0. They both involve m, so that means y double dot must equal minus g. The acceleration is equal to your gravitational constant going down. Shocking?
Nope.
No, but I would like to submit to you that's a pretty elegant way to get it. Okay, so I do this just to let you see it handles the easy cases quite nicely, doesn't it? And so what you are used to, what you have seen, I submit to you I don't think they did it any easier than this, and it probably was more convoluted the first time you had to encounter it. Okay? So it's elegant. Let's take a look a step up. What if I want to constrain my little mass to a particular motion? Is it okay if I erase this?
Yeah.
Now I've got a mass in a gravitational field again, but this time I'm going to constrain it by a string fixed about some point. And that string is of length L. What are we setting up here?
A pendulum.
It's a pendulum problem. Now this was kind of ugly when you first had to deal with it, right? You had to worry about all these kinds of blah, 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 whatever's going on, things of that sort, right? I submit to you it's going to be a little bit easier for us. All right? It's got some angle theta that it's been displaced, and I release it. Now, before you had to worry about resolving forces and all kinds of different directions and stuff. But I don't have to worry about that. I can do generalized coordinate. What would be the best way to express this, since all I care about is the motion?
Coordinates would be at the very top.
Yeah, and I would use r theta, not xy, right? I mean, because for this type of system, you cannot get much better than r theta. Because what's it changing in the r direction?
No.
It's not. It's the whole point of the string, right? So it's only going to be moving in the theta direction. So I only have one direction to worry about now. Instead of being a two-dimensional problem, it's a one-dimensional problem. That's kind of nice, isn't it? So I can ask, what is the kinetic energy of this ball? Now the kinetic energy, you're used to writing it kind of in linear type of things. We realize there's also rotational kinetic energy, right? So just like we have for linear things, we have 1/2 mv squared, right? I can also ask you the reasonable question, what is mass? What is it?
It's a volume. I mean, it's
No,
Right.
it's a relationship between volume and density, perhaps.
That's one way you can think about it, but right, when you start looking at things relativistically, that kind of goes away as a bad idea, right?
Yeah.
Right? Because, I mean, depending on, my particular velocity of whatever, reference frame I'm looking at, I can get all kinds of different things going on here. Okay? Because you can have mass change and all kinds of things. If I'm dealing with, I solve this problem from a reference frame traveling at the speed of light. Right? So, and you might say, why would I ever want to do that? Well, if I ever wanted to solve this problem on one of those famous two spaceships are traveling in the opposite direction of the speed, right? What if I want to put a pendulum on one of them and ask you what is that pendulum look like it's rotating from the other ship? Right? Now that may be a weird question to ask in our perspective, but it's reasonable. Okay? If it works, it ought to be handleable. So really when we're talking about mass, we're talking about a concept of an inertia, right? A resistance to being changed that's going on. Because acceleration is talking about how you are changing something, and mass is telling you in some sense, how does it resist that?
Okay.
And so what we're really getting in a sense on this, when you go to relativistic things, is it's saying that resistance in some sense does matter how the reference frames are looking at each other. It'll all work out, but you do have to take that into consideration. Now, from our case, we're going to just assume we're in the same room with it and all kinds of nice stuff like that. But that's what this is really telling you. Okay? So you really have 1/2 times an inertia times in some sense how fast is it doing the thing squared. Make sense? Now, rotationally, what is your inertia? It's no longer mass, is it? Because if it were just mass, then it shouldn't matter the position of my body. Correct?
Right.
Right? I should be able to change my body shape. My mass doesn't change when I stick my arms out, does it?
No.
So therefore, if I am rotating, right, it shouldn't matter if I lift my arms out. Correct? If it was just mass, it wouldn't matter, would it? Has anybody ever watched skating? Right? Now, why do I pick skating?
Because you take advantage of it.
Number one, people spin a lot in it. Number two, people watch it, so you have some experience with it. Number three, they're fairly frictionless. A good pair of skates is going to give you something where you're not dealing with like me spinning here. You have to deal with how well am I actually pushing against the floor and all kinds of stuff like that and slippage, things of this sort. So it removes a lot of that kind of ugliness and gets to a pretty simple thing. So what happens when a skater comes in and then they pull their arms in? It's spin faster. But I thought if it was just mass, it wouldn't do that, would it? Yeah, because it's not just mass. Your resistance to rotation is not your mass. It is related to your mass, but it is not purely your mass. Okay? We have a thing called rotational inertia, which has to do with where the mass is located relative to the center of your spinning. Right? If you are a point spinning about your axis, what's your rotational inertia? A point, a pure point in space, rotating about its axis.
Zero.
Zero.
Nothing.
Right? Why?
Because there's no, from your center of mass to your longest point is a fixed distance of r.
Yeah, so it actually has to do with the distance to the mass squared. As it goes for a point mass, there is no distribution. It's right at one point. If it's spinning about it, that would practically be zero. But think about it from another perspective. I've got a point mass and I tell you it's spinning. How do you know?
Do you really know?
Right? I mean, think seriously about it. I mean, how can you tell a point spinning? It may seem like a weird question, but realistically, it is a problem within our physical system, right? If you cannot in any way, shape, or form tell that it's spinning, perhaps it's not. Maybe it is. How do you know if that's spinning? Right? These are all questions beyond your ability to really deal with that goes on. Right? But the fact that it is an inertia of zero means they're cute, and somebody can argue about it in philosophy class, but it doesn't affect us. Okay? We can write on happily again. It doesn't mean everything you do in philosophy class can be ignored. Right? That's not my comment. My comment is, in this case, it's a neat concept, but it's a concept that will not affect your equations. Right? So you got to realize when things affect your equations and when they don't affect your equations. In that case, it won't matter, will it?
No.
Right? But if I took that same mass and I put it in orbit about me, right? There's what's called the parallel axis theorem. And that would tell me that for that mass, point mass m, rotating at a distance r from me, it would be mr squared. Sound reasonable? Right? And you could go through and you could start calculating these. We actually calculate them by taking the integrals of, the various moments about different axes, and you integrate it over the volume, and you'll get these various shapes, and you have to integrate the shell. So you can get one that's a ball of a particular width or whatever we want. Right? But all of these are equal to the rotational inertia, whatever you end up with. This is rotational inertia of a point about an axis r away from it. Right? If you get a rotation of a rod about one of its ends, and the rod is length L and mass m, then the rotational inertia of that is 1/3 mL squared. Because realize if I had made this mass, or this the mass of the rod 0 and then put the ball out here, it would be that. But since it's distributed across it, there's some parts of it that are doing absolutely nothing. Right? And some that are affecting full, but it's distributed. So when you integrate across the whole thing, this is what you get. Okay? So, and you could do you could solve this. These are tabulated out there as it goes on. And usually physics has fun making you do these whenever you get around to it. I don't know when they make you get around to
The
this.
first class, 221.
Do they? Okay,
Yeah.
awesome. Good. So then you should be familiar with those as an idea, right? But realize what that is it's telling you how hard is it to rotate you. Okay? This becomes very important when you start designing things because different shapes, the way you distribute the mass will affect it. Right? If I have a rod like this, it's different than if I have an I-beam. Okay? And this becomes important because this will affect, the behavior of the system. Right? I-beams are a little stronger for their mass distribution, but they'll have a little bit higher rotational inertia too. Right? Life is trade-offs as it goes. So, but in a sense, I kind of functions like our mass. But now, for rotational things, it's no longer a straight velocity. What is our rotational velocity? Yeah, we call it omega. We usually use omega for when we're sticking directions and everything else on it. So we go omega cross r and all that kind of thing gives me where it goes. I'm just going to do a pure kinetic energy. I don't care about the directions or all that kinds of other stuff. I just care about the amount, the magnitude. So in that case, we usually call it theta dot. And the reason why we use theta dot rather than omega is just we use omega to specifically include directional information. And once I am taking this is when I do the theta dot, but then it's got to be squared, just like velocity was squared. If you took your regular definition of omega and took the 2 norms squared, you get the same thing. Okay? But then I'd have to write norms in here. Now, that's not necessarily a bad thing to do in the long run. I think understanding that your energy is actually related to the 2 norms squared is a nice feature. It's another spot where you kind of see the Pythagorean stuff coming through again. Yeah.
So sure I got my notes correct. 1/2 I theta dot squared is the rotational kinetic energy.
Yeah. Now, and I'm just going to use I know the book, when at least the first edition of the book, when I looked at it, goes through and actually substitutes what that is. I don't want to do that. And the reason why I don't want to do that is because it's better to deal with it by what it is, because then different configurations, different setups, you can just look it up in a table and substitute in. That's a nice feature to be able to say, oh, it's not a rod, it's just a this. We can develop the entire solutions in terms of I, and then you can substitute it in the end without having to do the calculations. There's another nice feature about this, is I can take a look at this rotational inertia. And let's say for a second, minor digression here, right? What if I took that same thing, and let's say I called it a rod now with a mass on the end, but I put a small motor on this that can generate some amount of torque. Now, have you ever taken a motor and spun it?
Yeah.
It has some resistance to you spinning it too, doesn't it? So that motor, in addition to the rod having an I, the motor has some I for the motor. There's some I for the motor and there's an I for the rod. Okay? Now, if there's a big ball in the end, there's also an I for whatever that ball is rotating about that point. Okay? Now, in addition to this motor, what if this motor isn't directly connected here? What if I connect this through a series of gears? Right, so I have a gear here, and I have some other gears. So I have some gear chain that's going in, and that connects to my motor. So I can get some gear ratio. Do we ever want to do that kind of stuff?
Yeah.
I ever do it all the time, right? I mean, your servos are geared. Anything else geared?
Every motor essentially.
Yeah, think about when you drive here, right? Whether you have a manual or an automatic transmission or whatever you want, it's got a transmission. It's a series of gears to allow you to do trade-offs between your torque and your rotational speeds and everything else, right? So we often want to connect gear chains in here, sometimes even substituting different ones out. Well, in this case, it's no longer just I of the motor, it's I of the motor times the gears ratio squared. That's pretty easy to deal with. Now, assuming all of these are about the same rotational point that's going on, all I have to do is say the overall I is just the sum of those things. Right? I of the rod plus I of the B plus G squared, I of the motor. Right? Just add them up. That's my net rotational inertia about that point. Okay? I just call that I and I stick it in there. So if you want to add more stuff to it, if you want to make the problem look complicated, it's really easy to actually do if you leave it as I. However, if you solve it using a particular value for the rod, and then look at the answer, and then you try to say, you know, okay, now add, you know, a motor with a gear train in it. Now you're going to look at it and you're like, oh, I have no idea, right? And reasonably so, you just have to resolve the problem. So I submit to you it is much better to leave it as I, which is usually what is not done by a lot of people. Okay? But this is my argument for doing it slightly different. And then at the very end, substitute. Fair enough?
Mm-hmm. Now, is the gear ratio something that's given with the gears, or is that something that you have to calculate?
It would depend. If you get a package system, they might give you the gear ratio and the base for the motor, or you might be able to look up on the spec sheet and just find out what the net value is. Because they might just tell you, hey, the ratio for this whole thing, right, or the inertia for the entire servo is blah, blah, which would be the whole value, you know,
okay.
Gear chain together. So, you know, they could report however they wanted to. They could either tell you G and tell you the motor that's underneath. They could tell you what G squared I is and just tell you this is, you know, the I of this setup as it goes on. No problems. It's usually actually easier for them to report the net result. Anybody got any idea why that would be easier to do? I don't have to actually calculate that. I can measure it after you build it, right? Why would that be an advantage? Yeah, I mean, I can measure a whole bunch of these and kind of average them out. Realize when I make this value right here, I've actually assumed that these gears are massless.
Yeah.
Right? And they're on frictionless bearings connecting them. Okay? Because realize all I did is I used the gear ratio. I didn't add anything for them. Technically, there are rotational inertias for all those gears. That's probably tiny compared to the motor itself. But that's not necessarily always true. Okay? So it would be a lot easier to just kind of build the thing up. Now I might ballpark it by doing this when I'm initially setting it up. And if I were simulating it, I'd ballpark it again. But realize it's an approximation because I've skipped some terms. I dropped them out for simplicity's sake. Now if you actually go and measure the thing, then you have the exact value and you don't have to worry about it. The only nice thing about this type of area is it's easy to see, well, what if I swap the gear ratio out and changed it? You get an idea how it changes. We feel good with this little bit of a digression here on, right? My goal is for you to understand where I came from. and why it matters to us and how you can alter it on different situations. Okay. So now we come back. Okay, so this gives me the kinetic energy of my pendulum in terms of my theta direction. We agree? Okay, how about my potential energy? Well, my potential energy, this is a gravitational field, right? I could look at this. This would be the motion of it. If I went straight across here, this side, right here, that is L cosine theta. Do we agree? Nothing really fancy. This side is L, right? And that's theta, so this side has to be L cos theta.
Yep.
But the actual height that I want is here, right?
So it's all
So if I just take this, I can realize this whole side here is just L, right? Because it's the length of the string. So the particular height has to be L minus L cos theta.
Yep.
So your height is L 1 minus cosine theta. You agree? That that's the height at any particular point? If theta is 0 right down here, right? That's height is 0. So I've implicitly picked that as my origin. Could I have picked somewhere else? Yeah, of course I could have. Would it have been as nice? No. Right? Could I do it? Yes. Will the equations work out? Yes. Right? But, you know, why do it? Pick the easiest thing. Right? As it goes on. Now notice, I just picked whatever was easiest and let the coordinate system fall in as it may. And that's the nice advantage that comes in from dealing with generalized coordinates in a Lagrangian system. I don't have to guess what is the perfect coordinate system. I pick what is easiest, and the coordinate system falls out. Right? So that's kind of a nice feature of what's going on. So we agree that's the height, so what is the potential energy?
That times G.
Well, I have to have, you know, my mass times G times the height, mgh, right? And so that has to be my Lagrangian. Do we agree?
Yes.
Yes. Okay. So we're happy with this. Now, in this case, what's my variable? It's theta, so it's theta and theta dot. So I don't have to do this in terms of y anymore. The relevant variable is theta, and therefore theta dot. This is my Lagrangian. Let's do it. All right? So, first off, we'll start with theta. It's kind of easy as we go. So take the derivative of this whole thing. Derivative of this with respect to theta is? 0. Derivative of this with respect to theta? mgl. We'll get the minuses and the sign in a sec, right? Right? So, yeah, it's, okay. So I take mgl, that's just a constant. So I have to take the derivative of this. Well, derivative of that's 0. Derivative of this is?
Sine.
Right? So this will give me sine, right? It's a negative sign from the cosine, but double negatives. Right? So it's a minus a negative sign, therefore sine.
Wait, the derivative of negative cosine is positive sine.
Yes.
Yeah. Derivative of cosine
Yeah.
is minus sine. But a minus.
I can math. Okay, I
Right? So minus
mean, I'll give you a check.
cosine, so we leave the minus out.
That has to do with
I take the derivative, that's a constant, the minus 1. That's minus sine, so I get minus a negative sine theta.
It's all coming back.
Okay?
Magic.
Awesome. Okay, and this has a minus in front, and I got a minus there. Good? All right. Now we take the derivative with respect to theta dot. Right? This term goes, it doesn't involve theta dot.
Right.
How about this term? Well, I've got the 1/2 I And I get 2 times the 1/2 I, so I just get the I. We agree with that? So I end up with I, right? Theta dot. Answer with respect to theta dot, so I'm done. So we agree that this is the partial of L with respect to theta dot.
Yes.
Then I have to take the time derivative of that. Right? And that is equal to 0. Okay? So if you look, and you look back in your notes on what is the equation for the motion of a pendulum, that's it. That is exactly what you got before. Now, most physicists at this point go small angle approximation. And they just say, assuming you only displace it a little, then they replace sine theta by theta. Because at that point, it looks like an easy equation. You have I theta double dot plus MGL theta. Right? So there's usually people then take this, realize you don't have to actually solve this, but just so you recognize it is the same thing that goes on. Right? I've got I theta double dot, and we approximate this by plus MGL theta. Right? And we assume that that is equal to our 0 as it goes on. And then we want to solve this for theta. Now, if you notice, I've got a second derivative and the actual function itself, no first derivative, so it's pure simple harmonic motion. So this is going to be proportional to those terms. And you can just get the MGL, and it's on here, so you get the square root. So the frequency is going to be proportional to the square root of that MGL. Right.
Theta has to be in radians, correct? I remember it's small angle approximation.
Does it have to be in radians?
No,
If
but-
you don't, then you have to get these weird pi conversion factors,
Yeah.
which end up effectively putting you into radians. Okay? So the whole point of this is if you calculate this in radians, you don't have to worry about those ugly other terms,
Yeah.
right? Which account for all the conversions. This is part of why I say radians are the correct system of the universe. It doesn't involve me having to put some stupid weights in there to adjust for an arbitrary choice on our part. So I would encourage you just, I mean, you know, when nobody knew any better, it made perfect sense to use whatever happened to be easy. Once we've seen the equations and we realize it makes our life really difficult to use anything other than radians when you're actually calculating something, at that point there's really no excuse to do anything but radians. So you take this and realize this is normally, you know, your something that's going to look like if it's a ball and string, it's ml squared. Right? So when you divide these ones out together, the m's cancel, and you end up with a g over L. So you get the square root of GL when you're solving the whole thing, and that gives you your frequency. If you look up, that's, you know, where you get your period of oscillation off of them. So what is omega as it goes on. So I just mentioned that that's what you developed in physics. Now in our case, I don't need this. As a matter of fact, I'd encourage you not to go this way. And the reason why is for our sakes, you can't guarantee that small.
Right.
For a robotic arm. Right? That's going on. Right? As you're going, how do I know where I want that pendulum swinging? Right, so this only works. Anybody have an idea about what the theta works for? We'll just do it simple because most people kind of think degree terms, so just in degrees, where most people are thinking. About how big does, you know, that small angle approximation work?
60 degrees.
I thought it was less than
About
that.
5 degrees.
5 degrees, at that point you're pretty significantly off, but that's the last one where people say it holds, but you're at about easy 10% error at that point.
Wow.
Yeah, it's significant. And it's non-linear, so it's going to get worse as time goes on,
Yeah. And we're
as it's going on. Yeah, you're already pushing the edge of that envelope. So, you know, you can do up to 5 degrees and get something, a general indication of where it's going. People usually say under a degree is accurate for most systems. Like if I'm trying to do a robot, like a rocket or something, and I want to consider the rocket's deflection, if it's under a degree, I'm not going to worry about the errors at that point. Now, you know, realize they can still build. I have to do something to control them, but it's going to be reasonably accurate as it's going on. You get, it's sometimes people take up to 2.5 degrees. 5, like I said, is upper limits. Now realize if I'm dealing with a system with a pendulum on a cart or something of that sort, you cannot consider that it's likely going to be that small, okay, where that linear approximation is any darn good. And this is why when people started, when they first did the approximation, if you ever look at the pendulums that go on inside of like a museum or something like that to knock them over, they always have them ridiculously long so that you're getting a very small motion that's going on there. And then other effects come in, like the Coriolis effect that we didn't consider. You're actually on a rotating body. So those ones will swamp it bigger than this, so you figure that at that point you're not really doing too badly. Because you're down at the upper limits of this one's error, but you skip terms, so there's errors there too. So just consider you're close. Reasonable? So if you notice, it didn't take us much at all to derive this equation. It just took me more to actually motivate to you how the stupid thing worked. Right? And why does it make sense? We can do even more involved things than this. We're good with this? Step up to another tougher problem?
Yes.
Okay. So since we're dealing with pendulums, let's go to the next step of fun. Let me invert my pendulum and stick it on top of a cart that's driving around on a plane. All right, so I've got some mass m1 here, and here's the vertical direction. And I've got a pendulum. We'll assume the rod is weight 0. So I've got some mass 2 here and some angle theta. Now obviously as this pendulum is kind of displaced here, it's going to want to fall, which is going to want to push the cart. The cart has some motion, which might right the pendulum too. That's kind of a fun little system, right? Now imagine writing that using Newtonian. Yeah, right? I mean, you'll rapidly realize, that would be a nightmare to go through. Just being practical here. Now, when I look at this, what's the easiest ways to consider my motion here? Because we've got to kind of consider what is our generalized coordinate systems I want to resolve things out into.
Well, you've got two things going on. You've got an XY coordinate and you've got a polar coordinate, so which would be more efficient?
Yeah, so now you got to kind of pick out which one you think matters the most. So think about where I might be trying to use this, and this will kind of tell me where do I want to resolve it down to. Now, if I'm dealing with this, likely the one thing I can control is the motion of the car.
Right.
Yeah.
Does that make sense? So the motion of the car is constrained to a particular dimension, isn't it?
Mm-hmm.
It's constrained to x motion. The only thing that can move in y is the ball can fall on the end of that. Do we agree?
Yeah.
Okay. So I would submit to you that the most natural one to resolve this one into is xy. And the reason is, in all likelihood, what I'm controlling is the motion of this cart to keep the pendulum on. Right? If I could somehow, if I knew a motor here, and I could twist the motor, right? And by twisting the motor, I wanted to find out where did the car end up, I'd probably resolve it into polar coordinates and let the chips fall where they may. Okay? But in this case, I most likely can control the position of the car, position and velocity, and then go from there. And that's usually how this problem is set up, right? You take, like a toy train set or something, it can go forward and backward, and you put a, rigid rod with a ball on top of it, and you say balance this by moving the train forward and back. So it would make sense to resolve things into XY coordinates. Reasonable? Mm-hmm. Okay. So that's how I'm going to break this one down. Now, I'm going to take a look. I've got a kinetic energy of this. I've got the ball moving and stuff like this. So I can now ask you questions like, what's the kinetic energy of the cart?
1/2 m².
1/2 m.
1/2 m, but its velocity is all
X dot.
in the x, so it's got to be x dot squared. Do we agree? And I should say m1,
Yeah.
since that's the mass of the cart. All right, just to keep them separate. Do we agree that's kinetic energy of the cart? Okay. What's the kinetic energy of the pendulum? Now, I'm going to give you a massless rod. Right? Now, this doesn't really matter because that would be the I as it goes in. You know, but we usually say massless rod, and I got a point mass at the end. So I would know that my I was equal to the ml squared. In this case, we can just pick our I as it's going on. But I've got to resolve this into the velocity into two different components, right?
So just V or Vx.
We agree? It's, I mean, I've got its velocity in the x direction and then the one in the y. Yay? Okay. So, when we consider this as it goes on, this is, it's on a rod, so if this cart's moving, that's moving too. Right? And you assume it's moving at the same speed as the cart plus whatever the rotation due to theta dot is. So therefore, when I'm looking at that, I've got 1/2, right, my m2 as it's going on, and I now have an x dot. I'm going to get all my x1s and I'm going to get all my y1s. And then I can square them. Right? Because they're completely orthogonal directions, so there'll be no cross terms. So might as well take advantage of it. That make sense? Mm-hmm. Okay. So that is, right, so I've got x dot squared. That's due to the motion of this in that direction due to the movement of the cart. Now, what about my rotational movement? All right? Well, I've got to resolve this into x and y components too, don't I? Let me move this out of the way because it's kind of... All right, so if I took the motion of this here, this is tangential. All right, so if I kind of was able to draw decently, you know, some length L, and I drew a circle of that radius, right? Your velocity would be tangential to it. And at that particular point, I'll kind of draw it exaggerated, right? That is the particular velocity that it's got, right? The magnitude is going to be proportional to my theta dot times L, isn't it? We agree?
Yep.
So we know this is theta dot times L. Everybody does agree, yes? So then I can ask you to prove it to me. I mean, if you all agree, that means, I mean, you only agree when you can prove it. So think, how would I get that, right? Because why did I pick theta dot times L? Well, if you took a look at your velocity, right, of your rotation, it's your omega cross r, right? But I just want the actual magnitude of it, so I'm taking the 2 norm. Well, in this case, I'm not going to take the square of the 2 norm because it's going inside squares. All right, so I'll just, and that's it. But I'm going to be taking the norm of this as it goes. Well, the magnitude of this is theta dot. The magnitude of that is L. So since I'm only caring about the magnitudes on here, I'm not caring about the direction at this moment. Right? This is theta dot times a unit vector, and this is, right, L times a unit vector. Therefore, it's theta dot L in magnitude. Make more sense? So you ought to, in your head, have some reason why it's there. Right? If you don't, you're guessing. You might be guessing right, but you're guessing. Okay. So I can then ask, right, what is this particular component, the component in the x direction?
Theta dot L cosine theta.
Yeah, because this has to be theta, right? Huh? I mean, it's basic trig, right? So when you look at it in the x direction, I've got to add on to it, right, in L cosine theta times theta dot. And that's just, this side here is cosine theta times this side, which is just L theta dot. As a general rule, right, if you notice I've already separated things, I tend to put the things that are constant to the left and go to higher order derivatives on the right. So I tend to order them because I can. It's just scalar multiplication. So technically you could have written this as L theta dot cosine theta, right? And then I just moved it. Because everybody's staring at me like I did something strange really. Right? You know. My comment is if you write things in a particular way, it's easier to look for them later. Right? And I, in general, am going to want to sort in terms of the order of the derivative. So it's kind of nice to have my highest order derivative on the right-hand side. It's easy to find. To put constants on the left, when I'm going through and taking derivatives, which I'm going to have to do in a sec, it's nice to go, oh, that's a constant, forget it. So that's really why I bothered to do it. Make sense? Okay. Is there any other motion of this in the x direction?
No.
No. How about in the y direction?
Just the cosine theta.
No sine.
All right? I'm stated up. That's just what this side is, right? It's L theta dot times sine theta, and then I just always tend to sort my movement there. There? Now, if you notice, what you will get for this ball about the end, you might say, where is that rotational inertia? If I bothered to take this and look, right, on the far side where I'm dealing with the theta dot squared, the pure theta dot squared, the rotational term, I've got L squared times the M. ML squared is I. Right? But there is a cross term that goes on because it's, right, additive as it's going on. That's not the only velocity in that direction. If the cart was still, then that all it would be is just the rotational. Okay, do we agree this is my kinetic energy? All right, any potential energy in this system?
Sure.
Sure.
Okay, what?
That's,
Ball falling, right? So, this is the only thing that has any potential energy at all. What height is it?
L minus L sine theta.
It's not L sine theta.
No, L minus L sine theta, right? We got our total distance to the ball.
From the cart, right?
L minus L.
This is your height. Your ball is here. The height is therefore this side. Right? This part, this is your height. Do we agree? This is theta. That's your radius, L. So this has to be L cos theta.
Right. Next to matrix.
Right?
Not sine.
Sine is this side.
Yeah.
Now you notice it flipped because my angle over here is different. That's why this was cosine and sine. Because my angle was here once it rotates down on the sphere. But when I'm considering vertical displacement, the angle is pointing up. So therefore this side is the cosine side. Don't get fooled by it. Just draw a picture, right? So length L, cosine theta, it's got to be L cos theta is the height. Right? And it's mg h for gravitational potential energy, therefore mg L cos theta. Right. We good? So at this point, I now have my Lagrangian. All I have to do is take the appropriate derivatives. So remember, what we're going to want to do is partial with respect to, in this case, I'm just going to say my variable dotted dt minus partial with respect to the variable. That's what we're going to take them. And I can do them in different areas. Like for instance, I can take the derivative in the x direction. Right? I can take, right? So I can make my variable equal to x. And I can take the derivative of those with respect to my Lagrangian, and that's got it equal to 0 in the x, doesn't it?
Yeah.
I could do it in the y if I wanted, although it doesn't make a lot of sense in this case because we were able to resolve y out in terms of the other variables. I could do it in terms of theta. That's the other intelligent one. I've got two intelligent variables to take a respect to, x and theta. Because I get the theta dot, and I get the x dot from this part. So realize it's always true that this, as long as we got these nice conservative systems going on equal and all this beautiful stuff, right, has to be equal to L with respect to whatever variables I want to take. So if you've got multiple variables in play, you'll just get multiple differential equations. That's not too surprising. If you truly have some motion in a two-dimensional space, you're going to get an equation for x and an equation for y. Right? If you really have something that also involves, that's the center of the system moving and around it there's some, something spinning or whatever, then you're going to have motion in that spinning direction on top of that, as well as the center of mass for that system. So you would get equations for each individual motion that's going on. That's nice. This just resolves them out into each of the independent motions. I have one in the x and one in the theta. Good?
Am I missing something? I don't know. Where did the M1 go?
Did I?
Yeah, the thing under.
Oh, I forgot. Oh, I deleted it up there. Yeah, I was supposed to have included the 1/2 m. Thank you.
Okay.
So I had 1/2 m1
I was like scratching my
x
nose.
dot squared. Well, that's because I deleted the one up there. I thought I had copied it down, but I didn't.
And that's distinct from the x dot inside that big parenthetical.
Because this is the kinetic energy
of the card.
of the card.
Right.
This is the pendulum.
And then the other one's the Y.
And then this is the potential energy of the pendulum.
But the card is not attached.
So that last
Right.
M should be F2?
Yes. And I forgot to put the, because it's the pendulum falling. Right. So it's the mass that is relevant to that particular thing. Since it's the pendulum falling, it's got to be M2 because the card's potential energy is irrelevant. It has no chance of falling through the floor. Right? So there's no chance where this cart can ever change. Now, if this cart was on a thing with a hill or something in it, I could add that in. Based on where the cart was located, I could put in a potential energy term for the hill. Right? But realize that'd just be another potential energy term. In Newtonian stuff, that would make you just pull your hair out and run screaming from the room. Even I'd be like, oh hell. Just stick it in a package and let it work it out and let's hope for the best. But in Lagrangian, it's actually quite doable. Right? I'm not saying it won't be a complicated equation that comes out. I'm saying you can do it. You can get the difficult equation, which under Newtonian would really be quite an effort. Right? So in particular, like when I deleted a term because I accidentally erased it up top, you could see that I deleted a term because I accidentally erased it up top. That's the nice thing about this. It's verifiable. You don't have to worry about weird things. Oh, did you forget that force or whatever? And you don't have to worry about the coordinate systems of the forces or anything else. It just works. We good? You know where everything came from? All right, so this is kinetic. All right. So this is it. So I'm going to take it first with the x, which means my variable equals x.
Yeah.
So I have to take the partial with respect to x. Anything involving x?
A couple things. Actually, no.
No, that was pretty easy, wasn't it? Okay? So what it's telling you is, remember, the partial with respect to x is checking the potential energy in the x direction. It's telling you there's no potential energy in the x direction.
Which we know.
Which you knew that, right? So it's saying that the plane is infinitely flat, the cart slides along, and who cares? Okay, now we do the x dot. I've got one. All right? So I end up with this. The partial with respect to x dot of this term is?
Just M1.
M1 X.
All right? And I'm going to just note to myself I'm going to have to take the ddt of this whole thing. Because I want to write the whole thing out and then we'll take the derivative. I could actually do it piece by piece, but when I get to here I might have a lot of cross terms, so it's just going to be neater to write the whole thing out and then take the derivative of the whole thing. Okay, so that's the first term. Any other terms involving?
Yep.
Yeah, right here, just on the x. Now, realize I can distribute this so that this multiplies this term and this multiplies this, right? So, when I take a look at the x dot in here, I don't have to worry about that term.
Right.
Okay? And it doesn't involve that, there's no x dot. So it's just 1/2 m2 squared times this. Right? And I'm taking the derivative with respect to x dot there. All right, so x dot's inside this. So I'll get 2 times the constant outside. So I just get plus m2 times what was inside, x dot plus L cosine theta times theta dot times the derivative of x dot with respect to x dot, which is just 1. So I just neglect it.
Did you say 2 times? Is it 2 times?
2 times a half.
Oh, what's that? Okay.
I said 2 times the constant,
Yeah.
which just ends up being m2. Good? Okay. Any other terms involve x dot? No. Right? So this is what I'm taking the derivative with respect to time 2. That's got to be equal to 0. Take the time derivative now. Okay? So now I take the time derivative. So I get that, first off. Right? Now I got to take the time derivative of this. Mass isn't changing. Right? So now I take time derivative of what's inside. Well, I get this. That's trivial. Now I got to take the time derivative of this. It's going to be a little bit more work, right? Because it's a product of 2 different things that can be time varied. You've taken the partial, you've resulted in a function. Those functions involve variables with respect to time. All right, remember, these were only constants with respect to your x dot.
Right.
Not with respect to time. It's an ordinary derivative with respect to time. So, might need a little more room to take the derivative of this one. Okay, so I'm going to take the derivative with respect to theta dot first. And, you know, because it's the derivative of this one times that, plus the derivative of that times that one. I'm going to do the derivative of this one first. Anybody got an idea why? Because it's really easy, right? Because when I take the derivative of this one, I'm going to get a sign, and I don't want to erase anything.
Right.
So I'm just doing the one that involves me doing the least amount of rewriting. So now I have to take the derivative. I've got L cos theta, theta dot. Now I'm taking the derivative with respect to this one. Right? So plus, well, the L stays constant. Derivative of cosine is minus sine. But is it just minus sine?
And then you have to have a theta dot.
Times theta dot. Right? Because remember, this is theta of t.
Theta dot squared.
Right? Yes? Right? So it's not like if it was derivative of cosine of t with respect to t. I would agree with you, it would be minus sine of t. But it's a function of t, and that function of t is defined by the function theta of t. So therefore the derivative is sine of this, it's composition rule, right?
Yeah.
So it's the minus sine of theta t times the derivative of theta t with respect to t. That's this times theta dot. Yes?
Yeah.
Okay, that's where it came from. There you go. Yes?
Mm-hmm.
So this comes from taking a look in the x direction. Now if you notice, we want to try and get some feel for this. Right? If you look at this term, I could break this parentheses out and you would get m1 plus m2 times x double dot. That's kind of the net, if you just assume the whole thing was rigid. Okay? That's telling you, that rigid system, how would it move? Okay? The rest of these terms are accounting for it not being rigid as it's going. Right? So I've got the terms that are going to involve, right, what happens due to the rotation of that mass that's going on, what is its acceleration, and I've got the term that involves how it's moving, right, relative to its velocity.
Yeah.
Right? And there are two. This is, you know, your kind of your centripetal type forces or whatever you want to consider, and this is the actual rotation one. However you want to go through those and break them up. Make sense?
Mm-hmm.
So it's kind of expected. This one is kind of telling you the coupling between whatever is happening in the theta direction and what's going to result in x. So if I were solving for these, I would want to solve for x in terms of theta here. Right? If I'm driving the cart as it goes, I would want to solve for theta in terms of x. It's going to depend which way it goes. If I'm just leaving it alone, putting it in a position and let it drop, okay, to find out the final position of x the system has moved from that pendulum dropping and shoving things sideways, find x in terms of theta. If the cart has a motor on it and it's driving, I'd solve for theta in terms of x. Okay, so we got that one. What if I make my variable equal to theta? I'll get another set of equations that also must hold, won't I? Okay. How does this depend on theta? Doesn't. Right? No theta there. Theta and the rest? Yeah, there's theta, there's theta, there's theta. I can't avoid theta at this point, can I? Right? That's going to be kind of big and ugly. And this is what you would kind of expect, that a lot of this is in the motion of the pendulum itself. This is where the nonlinearity goes on. Right? That one, this equation was kind of telling me what's happening to the center of mass of that system, but it wasn't telling me what was actually going on with the pendulum. This is just telling me what's the resultant, you know, effect on that system of where it's positioned. Not giving me a real strict thing of pendulum motion as it goes. So now I take the derivative with respect to theta, right? And that's going to give me a potential. I'm going to have to take the derivative with respect to theta dot for the kinetic. I don't think there's anything simple about it, so I'm just going to do it in terms of theta dot first. Right? Reason being that we just always do the theta dot one first, and it's not going to be a small term the other way, so I'll run out of space. Right? So just to keep the order here, normally I can just take this one, which is normally simple. In this case, it's not simple. I can't just stick something to the left. That's why I'm switching my normal ordering as it goes, because it's not pretty, it's not small. Okay, so take it with respect to theta dot. All right, again, this term is irrelevant to me, so I come on to here. All right? So the derivative of this with respect to theta dot, again, my theta dot's inside here. Now I could pull if I felt like theta dot's out, but that'd have cross terms, so I might as well just resolve them separately.
Right.
So I'm going to get m2, right, times my function, which is x dot plus L cosine theta, right, times theta dot. Right, that's the derivative of this whole thing, and then it's times the derivative of the inner function, right? That's composition rule, right? Because I just took the derivative with respect to the square. Now I've got to take with respect to what's inside the square, which will just be L cos theta.
Yeah, that's the coefficient of theta dot.
Right? Because that's just this part here, right? Remember, this is the derivative with respect to 1/2 m some variable squiggle squared. Because a lot of people are staring at me again like, oh my God, right? I get the 2 times 1/2 m squiggle,
Times d squared.
right? When I'm taking it with respect to some other, this is in terms of whatever squiggle is, right? Now, if it was in terms of some squiggle of some other variable, you know, whatever I want to call it, variable v or whatever, now I'm taking the derivative with respect to this. It's still this times, right, whatever, right, my partial of squiggle with respect to v, because I'm taking partials at this moment as it's going on. Right? That's just composition rule, right? Or chain rule, however you want to call the thing. I like to call it composition because the underlying thing is composition. It ends up chaining them together, but it's really a composition of functions, right? And so you just kind of work the outside and keep nesting them within, break them down into simple little pieces. It makes life much simpler. Huh? Do we agree with getting this? You ever wondered why did you have to take a bunch of calculus? This is why, right? And you may say this is not simple. I never said it was not going to involve a lot of calculations. I said it's doable. As opposed to if you had to write this out in Newtonian mechanics, this would take you all night. Right? If you even get it correct. Okay, so I've now taken the partial with respect to theta dot. Remember, I'm still going to have to take the derivative with respect to time of these things. All right, so maybe I should note that because I'm doing the first one, d dt of this. So that's this one. How about that one? You guys help me out with this. This way I know you're...
I'm sorry, should one of those cosines be signed?
No.
No.
Okay.
Yeah, the first one is.
Okay.
I love that.
So you don't believe me.
Yeah.
So, and that's good. You don't have to believe me. But the answer is no, it shouldn't.
Okay.
Now, your next question should be why, right?
That's gotta be why.
Yes. No. You know, the reason is I'm not taking the derivative with respect to theta. So this is a constant. L cos theta is a constant.
You're doing theta dot.
I'm doing with respect to theta dot.
I'm doing theta. That's like I confused.
I said, let me start with theta dot.
Yeah.
Because I'm going to go left to right through here. Often I like to start with this one because it's usually simpler to take that derivative.
Okay.
Okay? But in this case, with all the cross terms, and theta appears in every single term, if I did the derivative with respect to theta, and I left a little bit of room, I just run out of room. So the only reason I'm kind of going the other way is just because, you know, everybody always says, oh, it's evil, you know, you got a whiteboard, you can just shove stuff in. That's true. So I'm trying not to be evil on whiteboard use. You know. Okay. Do we agree with the first term?
Yeah.
Then you ought to be able to do the second part of that term for me.
Just L sine theta dot. Oh, yes, giant.
Don't forget the
collection of
enclosing parentheses. You have to distribute that 1/2 m2 to both terms.
amalgamation
Right.
of stuff.
Enclosing. All right? So you get the 2 times 1/2 m2 just gives you the m2. Okay. Now what was the rest of yours?
L sine theta.
L sine theta dot.
Outside theta.
Yeah, and L sine theta dot.
Yep. Silly composition stuff.
Good old.
I'm happy with that.
Okay.
What? Awesome. Okay, so we've now gone through that much, but this one here does not involve theta dot. So that's the end of that. I'm just going to do the minus partial with respect to theta right now, and then we can do this one because this is going to, again, it'll explode when I take the time to do it. So let's just at least finish this so it doesn't become unreadable. So I've got to do minus, and then I've got a negative. Right? Oh, actually, I should just start at the end. I'm going to just do minus and we'll do the whole thing. Because I, again, have a lot of terms, don't I?
Yeah.
Yeah, so let's take a look. I'm now taking theta as my variable, but it's inside. All right? So I therefore have to take the derivative of this whole square term to get at it. So I'm going to end up with m2 x dot plus L cosine theta, theta dot. That's the function. Now I have to take the derivative of what's inside the square.
Minus.
What's inside the square is going to give me minus L sine theta, right, times the theta dot, which is a constant, times the theta dot from it with, or actually, yeah, oh, it's just with respect to theta, so it's theta. There's no time derivative in this case. Do we agree? That's for the first term. All right? So this comes from this one times that.
Right.
Partial with respect to the variable. All right? I told you it's big.
Yeah.
But imagine trying to figure these out all by trig. Okay? At least in this sense, it's taking care of it all for you. This is where I argue to you that it's the biggest use. You might go, this is still pretty ugly. However, getting this function, just as a note, because I know there's a lot of people going, oh my God, right? In reality, I just wouldn't have to even worry about this. Why?
Throw it in MATLAB.
Right? There's a symbolic algebra packages.
Oh yeah.
Right? As long as I can get the kinetic energy equation that's going on, symbolic algebra packages can solve that. Right? So you draw it up in CAD and it can all directly fall out. It's very easy to write up the energy equation, and then I could go into Mathematica, right? I can go into all kinds of different, anybody that has a symbolic solver for it, Maple, right? Whichever package has symbolic, and I would do symbolic if it was. MATLAB uses Maple for its symbolic solutions. Right? So there's a number of these ones that are symbolic algebra solvers. Just put the function in and let it go. Right? Now at that point, your biggest thing, it's going to give you this big old nasty expressions. It'll just drop out for you. Right? Because it can do that. At that point, you've got to know, is it right? Okay? Because it's going to give you this huge thing. You might go, well, I'd have to then calculate the whole thing. Or you'd have to be able to look at it and see if everything correct is there.
Right.
You have to say, does this follow through? Now, how many people honestly think you're really going to do that?
What, check it or?
Yeah.
I mean, it's not that hard
Check
to
it.
check. I mean, you just see what terms you're expecting because,
Yeah. Does it ever happen that problems go on?
yeah.
Yeah. Unfortunately, it does.
The beautiful
I-
thing about
I
that
mean-
though is like they get really, really wrong when you punch them into like a black box situation. I don't ever get just one thing changing for
You know,
me.
I mean, number one, if you mess something up on this
So you'd
side,
be able
it's
to see
possible
it.
for user error to screw it up.
Yeah.
Okay? But beyond that, it is also happens that sometimes those symbolic solvers are wrong.
Oh.
Okay? There was a really big one that happened with Mathematica, which is the favorite choice of physicists, because Mathematica came from, what's his name, Wolfram. Is the guy who developed it. He's a famous physicist, so he kind of developed this as his claim to fame
Right.
as it goes on. And it turned out that, it's been a little while, but it actually integrated wrong on a number of terms. So in the 90s, there's this huge problem, and it would do it correctly sometimes, but in a bunch of cases, it would just fail completely and miserably. Okay? And for a while, they denied it, and they were kind of stuck with it, and, people have always found little errors that creep in. So my suggestion to you is it can be wrong. So the biggest skill you can walk away with, number one, is having done it once, so you can go, okay, I can do it. Number two, how do I do it? Okay. So that's from the first one, correct?
Mm-hmm.
So you ought to be able to do the second one for me.
Yeah.
I agree. So what would that be? Second one is this term.
Right. So just sine to cosine's not a negative, so just
M2. I guess don't forget, this multiplies that,
yes.
right?
L cosine theta. Or shoot. Yeah, on that side. I guess it doesn't matter what particular order, but yeah.
I'll put the parentheses to kind of group them up, right? This is inside the square, and this is the derivative of what's inside the square with respect to theta.
Yes.
Don't we put the theta dot after in that last part here? Because there's a theta dot.
He's already done it there. Yeah.
It's what's inside.
So
So the, oh yeah, you mean out here?
Yeah.
Yes,
Exactly.
yes, there should be, right? Times theta dot. Right? Good? So that's that term. But then I still have theta with respect to this. This is where your potential energy comes in. Right? So now I've got minus built into it. M2GL. Derivative of cosine theta is and this is closing this parentheses. Then you just have to distribute the minus. Now realize this is a big ugly expression, but it really wasn't that hard, was it? Right? It was tedious, however. Right? Tedious means good for a computer. Right? You are computer people, right? We do it once or twice and we go, ah, I understand. And I never want to do that again. Okay? Therefore we go, this is why everybody, whatever type of engineer, had better understand something about programming. All right. Good?
Mm-hmm.
Now, I could go through and take the derivative with respect to time of this, but I don't think it's necessarily informative to you, and I guess I'm out of time also. Yeah.
So what would be the next step after that? Do we just add?
So I would take
that
that this has to be equal to 0,
I mean, after.
right? I would take the derivative of this, I would get a big expression.
Yeah.
Then I would have two equations, and I would have my unknowns,
Oh, dear God.
right?
Yeah. Okay.
So at that point, that's when we go into a control system, how do we solve this? The easiest way you go, oh my God, that involves derivatives. I would take the Laplace transform of this. Then it becomes an algebraic equation. I rewrite it as a matrix with terms, and I would just stick it into a solver and be done with the whole silly thing. Okay? And it would be done in a shot. I mean, it would be, each individual term in the matrix would be gigantic. But, you know, who really cares? Right? So my point to you is I can get as complicated of a system as I want to get. And it will work out. Okay? Awesome. Have a lovely day.